Okay, so we continue with equilibrium cooling. Solidification in the solid and liquid phase occurs gradually upon cooling from the liquidus line, and the composition of the solid and the liquid change gradually during cooling. So as we saw from the different microstructures for the different points. So as you see, we're going down, we're cooling. So as we are cooling, there are different variations of the microstructure, and what we're seeing overall is an increase in the solid composition of solution. Of the metal. So the nuclei of the solid phase form and they grow to consume all the liquid as the liquid as that one also is critical. So now we move on to what is known as fast or non-equilibrium cooling. So we're going to look at the development of the microstructure in such isomorphous alloys that are cooled real quick or non-equilibrium. So this is basically this is a situation that we see in industry. For the industry, we usually just use fast cooling or non-equilibrium cooling. So same points as earlier, but we're just going to have some bit of variations in the microstructure. So again, you have our composition for all the points, as you can see in a straight line, so meaning they are the same overall composition, which is at 35 nickel, 35 weight percent. So 35% weight percent there. So for liquids, just like in the equilibrium cooling, it's just liquids. There are no solids at this point. As you begin to drop your temperature, you come to point B. Here with an accent, point B. What is happening? You have your formation now, the crystals are beginning to form, just like in the first one. Then, as you go down further to point C, at this point, as you can see, you have as you hit the liquidus line, your first crystals appear or solid particles appear. As you go down, what's happening? Because it's fast cooling, you're not allowing, there's no time for these ones to integrate the other crystals that are coming as a result of the cooling. That is very slow. When it's fast cooling, it simply means when you hit this line, there's these particles that form. The next point, what happens? The next ones, they just simply kind of form around the earlier particles. They're not really, there's no slow time for them to nicely integrate with the earlier solid particles, but they're just simply forming more or less like layers, just like an onion. Think of it as onion. So you have the smaller one there at the beginning, isn't it? Then the others covers forming up as you go. So initially your onion will be small, and then as you are cooling to the next point, what's happening is that you just have another layer now of onion covering your previous one, and so on and so forth. So by the time you come to point C, what you see inside there is what formed here, what formed here at 46, okay, or 46% weight percent nickel. So what forms here now is what is at a different, what is forming from C now is just simply layering itself on top of the already formed solids. By the time we come to point D here, point D is on the solidus line, we just simply have another layer forming up on these two previous layers, okay? So now what means? It means that you have three types. You have the first one here, then the second one forms on top of the first one, and then here there's a third one forming on top of these two. By the time you reach E, E, remember, is a point in the solid phase. So it's your solution is, or your method here is completely in solid form. And you just have simply another layer there. Okay, and by the time you come to F there, you just basically have more layers as you go. Just have more and more layers of the same. So some nucleation is forming at some point, but not much. What you're experiencing here is more of layering. More of layering. So as you can see, the microstructure will be different compared to the one that we observed in, you see how it formed here in the solids. You just have the grain boundaries, basically, but here you have different boundaries, for the different coolings, the stages in cooling that you had, that your metal had experienced. So what can we say about this fast cooling? The compositional changes require diffusion in solid and liquid phases. Diffusion in the solid state is very slow. The new layers that solidify on top of the existing grains have equilibrium composition at that temperature, but once they are solid, their composition does not change. Okay, so once they solidify, their composition does not change, does not allow for more crystals to form within them. No. And the formation of layered or poured grains and the invalidity of the tie line method to determine the composition of the solid phase. So for this one, you can't really use the tie method because of the formation of layered grains. Unlike the other one where you have your crystals integrating into the previously formed one very well, it's easy for it to pick the composition using the tie line method. What else? However, it still works for the liquid phase, the tie line method, where diffusion is fast. The average nickel content of solid grains is higher. However, the application of the lever rule gives us a greater proportion of the liquid phase as compared to the one for the equilibrium cooling at the same temperature. So there are variations also in results even with the liquid phase when it comes to the equilibrium cooling and the non-equilibrium cooling. And the solid line is shifted to the right, higher nickel content. Solidification is complete at the lower temperature, and the outer part of the grains are richer in the low melting component, which is copper. Okay, so as you are cooling down, nickel has a higher melting point than copper. So in the case of a solid, there where you have nickel and copper, it means that the first one, as you are cooling, the first particles that are formed are usually of the component, the first particles, solid particles that are formed are usually of the component that has the higher melting point. Then as you go down, so it means as you go down, that's when now the component with the lower melting point, this is when now its atoms now are beginning to form up a layer around the solid particles. So in the end, what you have is that the core of your crystals will be rich in nickel, while the outer core of you can call them grains, in this case, the outer core of your grains will be rich in copper. And upon heating, grain boundaries will melt first. So meaning it's very easy for your alloy to break at the grain boundaries, because at the boundaries, that's where you had the metal with the lowest with the lower melting points forming up, closing up. So it means with the low, as you are beginning to heat it, it will quickly melt from the boundaries there with for the fast cooling. So upon heating, grain boundaries will melt first. This can lead to premature mechanical failure. I hope that point is clear. Let me get back to something that has some boundaries. So what is being talked about here is that the outer layer, as you can see, the outer layer there will be composed mainly of copper, the metal with a lower melting point. So it means that when this metal is now being subjected to any heat, any form of heat, it will start now melting in the boundaries. Or maybe the boundaries look better here. It will start melting from there quickly because that's where you have your copper. That's where you have your copper sitting along these boundaries. So it will be easy for your alloy to have, or for your metal to have a mechanical failure because it will first break at the boundaries. Okay, so we move on to what are known as binary eutectic systems. Binary eutectic systems. These are systems of alloys with limited.
I've got a question, madam.
Yes.
Doc, I've got a question.
Yes, please go ahead. Go ahead, please.
Is it correct to say that? Sorry, my connectivity is bad today. I'm in the bush.
Okay.
But is it correct to say that the cooling can affect the strength of the material? The two types of cooling, slow cooling and
yes, they affect the quality of your metal, of your alloys. If it's binary, I mean, if it's equilibrium, if it's slow cooling and if it's fast cooling. So with slow cooling, like we say, you allow, you know, the components, the atoms from the different components to integrate, to mix out, maybe use the word mix in well. Unlike with fast cooling, like we said, usually what happens is that the outer layer of your grains will be made up of the component with the lower melting point, such that when that particular piece of metal is subjected to heat, you're going to experience mechanical failure because right at the grains is where you are first going to experience the melting. Because at the grains, you just have one component, for example, copper in this case, which has a lower melting point than the nickel that it's alloyed with. So there's going to be a difference in terms of strength.
No, thank you. Understood.
All right. Okay, so move
forward. The other comment I wanted to make, Doc, is maybe it's an example. There's a time we had a project in the bush, so I had to buy axes, you know, axes for cutting trees. Yeah, so when we went to use those axes on the trees, they were bending, you know, they were like soft, they were bending. So one of the guys, the villagers said, no, you have to take it back. There's something he didn't do that that has to be done so that the axes can be stronger. So we took them back and then he had to reheat them, and then when we use and what in terms of what we are learning, what exactly was done that they don't really, I mean, they know they have been doing that for you know, but they don't really understand in terms of material science what exactly they were doing to the metal.
So that was hot working, huh? That they did, that they subjected it to. So there's what is known as cold working and hot working. So they subjected it. So what you were making a comment, just to. Hello.
Sorry, my network is quite bad. But what I'm saying is, I don't know if you can hear me.
I can hear you now.
Yes, yes. We bought axes, you know, for cutting trees.
Yes, yes, I understood you to say you took them back and then
Yes.
he heated them. He
Yes.
subjected the metal part
Yes,
of the
and
axe
put
to heat,
dirty
isn't it?
water or something like that.
And then he had to heat them, isn't it, with another piece of
Yes,
metal,
and then he had to
harden them.
use some dirty water or something like that. Yeah. Yes, that's true. That's true.
Yes,
Yes.
that's
He was
interesting.
using some dirty water, you know, he has to use some with yes. So I you know, ending now I'm
Okay, we've lost, I seem to have lost you there. I don't know if
trying to
you're
understand what exactly that oh my god, my network is terrible here.
Anyway, as we are going, we are going to understand it much better. In fact, what I can say about metal is that, you know, like for a long time, for centuries, for thousands of years, we have been working with, humans have worked with metals without really understanding their properties. Material science is a fairly new science, new field. Just in the early 20th century, that's when it was qualified as to be an independent discipline. But material science is something that we actually all had been studying before we even knew it, you know? And it's very interesting because a lot of what we learn in material science was just accidentally discovered, actually. There are very few components of what we call material science today that were actually specifically, you know, discovered in the lab. Most of it is just something that through the ages, through the centuries, man has just accidentally discovered and used to his advantage. People were using alloys, you know, before they even knew what alloys really were. So it's interesting. Anyway, I hope you found out what exactly it's called, what they were doing, what exactly they were achieving, or how they were achieving it anyway.
What I'm trying to think is that because before we took it back, the axe was soft. But after he did that procedure, it stopped bending. You know, the axe stopped bending. They became stronger. You know.
Yes.
So I'm sure maybe some addition of carbon or something like that. I wish I could go back and ask exactly what they did to the axe, but
no, what I do, I will not tell you what they did.
They were before we bought them. Yes.
I will not tell you what they did, but just for everyone, maybe I can throw it to everyone. Just let it be our homework. Let's all research on it. We're going to cover that topic also. It's coming. When we're going to look at the production of iron and steel, you understand it better. That is after this. But it's still okay for you to actually just do a research. Do some research on it. You'll be amazed. How atoms will behave when subjected to heat. And then also the issue of remember the FCCs and the BCCs, the face-centered cubic structures. So all that will come into play. So you can check it up as homework and try and find out, just do some research about it, but then we'll cover it also in class. I will agree, everyone, this goes to everyone. I think we're all going to find it interesting and we'll learn a thing or two from there. Okay, so we move forward. Looking at the binary text systems. So we're going to understand what makes them different from the other binary systems that we looked at. So these are systems alloys with limited, so this is the difference, limited solubility. With nickel and copper, they had unlimited solubility. Remember, solid solubility. But with this one, there is limited solubility, and there are also three-phase regions, just like the earlier one we looked at. So you have the solid solution alpha, In this case, as an example, you have silver in copper. This is a silver in copper matrix. So silver is dissolving into copper. And then you have the beta. This is a solid solution of copper in silver matrix. And then you have the liquid. So you have two types of solid solutions here. Let's put together. In this one, you have the alpha, which is the solid solution of alpha in copper. And then you have the beta, solid solution of copper in silver matrix. And then you have the liquid. So there are three two-phase regions. So you have the alpha plus L, which is the molten state. Alpha plus L. Remember, we had it even earlier. Then you have the beta plus L. So beta in this case is what? Solid solution of copper in silver. And then you have the alpha plus beta. So what is alpha plus beta? This is this earlier solution or solid solution of silver in copper and copper in silver. So these also will form a separate phase. So it means that, like I remember my earlier example when I was saying sometimes when you're cooling and then there's solidification happening and there's diffusion there, you have your other components dissolving into the other, so it reaches a limit. And then the other component that did not manage to dissolve into that other component will solidify outside the solution. So in the end, you end up achieving two solids within the solid. So the Sauvage line, there's what is known as the Sauvage line. We looked at the solid dust and the liquid dust, but then we have an introduction of a different type of line, which is known as the Sauvage line. This is a line which separates one solid solution from a mixture of solid solutions. I'll read that again. It separates one solid solution from a mixture of solid solutions. This Sauvage line shows the limit of solubility. Look at it in the diagram. So this is a diagram showing an alloy of copper and silver. So on the x-axis, we have the composition weight % of silver. Okay. 0 to 100. Then it means if silver is 20, it means copper is what? 80%. If silver is 80, copper is 20%. Then on the y-axis, we have temperature in degrees Celsius as usual. And you have our different temperatures here being depicted. Then we have our liquid dust line. So just like in the earlier one, this is our liquid dust line. This is also the liquid dust line. Okay. So meaning anything above this line here is known as the liquid phase. Liquid phase. Then we have what is known as the solid dust line. This is, sorry, the solid dust line. So this solid dust line is separating one solid from the other. So in this case, we have alpha here is one solid. So let's come back to this. What is the alpha solid solution? This is the solid solution of silver in copper matrix. And then this one is the beta solid, which is the matrix of copper and silver. Okay, so we have the alpha plus L, which is the molten state here, just like in our earlier one, depicting the solid plus the liquid phase combined. Then here we have the beta plus liquid, which is also a solid plus liquid phase, except this time we're not having alpha particles, but beta particles. So meaning these are solids belonging to another component, primarily belonging to another component, same as the alpha primarily belonging to a certain component. Okay, what else? There's this line here. This line is known as the eutectic line. Okay, so this horizontal line is known as the eutectic line, and it separates this intermediate phase from this, and this intermediate phase from the solid. So this is the solid phase, which is known as the alpha plus beta phase. So you have two types of solids here combined. There's the alpha solid plus the beta solid. Then this point E here is known as the eutectic point. So at this point, what it means that at this point, with a certain composition, so when you draw a line, so when you draw a line, a vertical line coming down, I think it should give us roughly something like 60 watts. 60, no, 70 something, I say 70. 73% probably, or 72% silver. At the composition of 73 weight percent silver here, this is where we have the eutectic point. What does a eutectic point mean? It means that at this point, this is a point where our alloy is going to move directly from liquid into a solid. I hope we get that, we understand that. So it simply means that if our point, okay, from moving from there, solidifying, isn't it, or cooling from this point here at 1000, roughly 1000 degrees Celsius, as we come down at this particular composition only, it means that once we hit the solid, that is also known as the solid dust line, the eutectic line, more or less the solid dust line. So once we hit the solid dust line here, we'll directly move into the solid phase. It means at this particular composition, at the eutectic point, your alloy will move directly from a liquid into a solid. It means it will not go through the intermediate phases. Are we together there? I hope we are. Okay, that's what is special about this particular point. It's also known as the invariant point. So the liquid and two solid phases coexist in equilibrium at the eutectic composition CE and the eutectic temperature. So this is the eutectic temperature going this way around the 700 and something, 780. That is the eutectic temperature, 779 degrees Celsius to be precise. That's the eutectic temperature. So this composition here at the eutectic point is known as the CE, okay? Then the eutectic isotherm, that is a horizontal solid dust line at TE. This solid, or the eutectic line, this one. This is the one that is being talked about here. That is the eutectic isotherm, the horizontal solid dust line at TE. Then we have the eutectic reaction. This is the transition between liquid and mixture of two solid phases. That's the eutectic reaction. That's a transition between liquid and mixture of two solid phases. That is the alpha plus beta at eutectic concentration of C. Basically, this reaction here where you have a movement direct from liquid to the solid. It's a very interesting point. The melting point of the eutectic alloy is lower than that of the component. So eutectic, it simply just means easy to melt. That's what it simply means. So at most, two phases can be in equilibrium within a phase field. Two phases can be in equilibrium within a phase field. These three phases, liquid, alpha, and beta, may be in equilibrium only at a few points along the eutectic isotherm. So in short, just at this is the equilibrium line. So at this point, and that point, Single phase regions are separated by two phase regions. Single phase regions are separated by two phase regions. This is a single phase region. Right? So this one is single phase, this one is single phase, and this one is single phase. So there's nowhere in this for eutectic systems would you have these ones in line with each other, the single ones? No, there's always an intermediate phase in between for them, either intermediate or this type of phase, alpha plus beta. So there's always either alpha plus L, alpha plus beta, or this particular one, alpha plus, sorry, L plus beta or alpha plus beta. This is what this means here. So compositions and relative amounts of phases are determined from the same tie lines and lever row as for isomorphous alloys. So the same way we're depicting, remember how we're doing to find the lever rows and so on and so forth. The same thing that we are applying even here. So the tie line, the same way will be drawn like that. So if you want to find the composition for point B, you draw your tie line there, and then you drop the vertical lines just the same way that we did our earlier on, like that. Anyway, something like this. And then we'll have our point there. We have to drop it also. So assuming it's 20, the lines are pretty bent. Anyway, something like this. So meaning if you want to find, this is alpha plus L1. So if you want to find the composition of the alpha particles, so alpha is this side. So we're going to get this distance divided by the overall distance here at the bottom. Over together, I'll say that again. To find the composition of alpha particles, we're going to get this distance divided by the overall distance. So for the top distance, it would be what? 50 what? 58, 57.
57.
Minus 19.
20.
Okay, let's go with 20. So 57 minus 20 divided by 57 minus, what's this point here? This is 10. Yeah, slightly before 10, it would be like 9 or 8, 9, 29. Yeah, so that's how we find it. For the liquid phase, we get that one divided by the overall. That's the way we did it with the same thing as this. For this one, we just pick one, isn't it? Because here it's not going to complete on the other side. But anyway, if there's a point inside here, we'll do the same thing. Where it's touching the boundary lines, where the tie line is touching the boundary lines, you drop them down, drop the verticals, plus the vertical from the point itself coming down, and then you do the math from there. So now we look at the development of the microstructure in eutectic alloys. So we have which points? We have this point H. I don't know if you can see it. There's a point H here, and there's a point L here. So for point H, it's clear, isn't it, liquid? So your microstructure will just basically be blank. So you just draw a circle and there'll be nothing inside. That's the microstructure here at H. When you look at the composition there, we drop this line coming down, it gives us something roughly 61.9 weight percent of tin. SN is tin here. Okay, so coming to point L is just below the solid line, this eutectic line. Just below it, it's in the alpha plus beta region. And for eutectic systems, you see they're not having the nucleus, the conventional nuclear formation like we had previously, but in this case, they're actually stripped. they actually form in strips. And as you can see, these strips here form. This is basically how the microstructure forms up. Then you have your grain boundaries there. So you have a grain boundary there, and then you have your solidification happening in form of strips, just like it's depicted here. So the earlier strips were from the previous temperature. Then as it came down now to finally partly here, you have the other ones coming in. We'll look at that going forward. So we picked, so this, let me show you something. We're going to look at points along the side, okay? Along the side. So it's just been expanded, zoomed it out, and then it's giving us this part here, just for us to better understand. So this is an alloy of lead and tin. So in this case of lead-rich alloy, 0.0 to 2% of tin. So meaning tin is there, there's a smaller percent. You can see 0 to 2% of tin. So meaning it's made out of roughly what? 99.8, 99.8 to 100% lead. That's the composition we're interested in here. So there's a point A here, point B there, point C over there. So we're going to look at the microstructure. Remember, the points are just roughly here at the beginning. That's why it's been expanded, because it's really tiny. 0.2 is really, really somewhere close. If we looked at it from here, we would not even see 0.2. That's why it's been expanded a bit. It's been zoomed out here, just to help us see where the 0.2 is lying. Okay, so point A is here. It's in the liquid phase. As you can see there, it's above there. So the liquid phase, again, your microstructure, you just draw a circle and there'll be nothing inside. Coming to point B, where is point B lying? Point B is within this intermediate phase. It's within alpha plus L phase. So your microstructure will be there and you have your solids there. The alpha particle solids. You have to pick alpha because there are two types of solids here. So you have to be, when you are drawing your solid particles, you have to indicate which particular solid you're talking about. There's the alpha solid and the beta solid. So here we're in the alpha, we're in this alpha region. So the solids in question here are the alpha solids. So that's how come you have the alpha there. Then point C, so you have your alpha here in point B, it's intermediate. You have a mixture of solid and liquid. So you have a liquid there, plus your alpha particles over there. Coming to point C, where is point C? Point C is in the alpha region. This is the solid region, okay? It's a solid region. Simply means that as you are cooling down below 300 degrees Celsius, coming close, as you are approaching 200, you already have a solid there formed. And it means basically that there's nucleation that has happened, and these particles grew around them till they met the other particles there, and then the difference in between them there, which is known as the boundaries, they are formed there, and you have the boundaries formed there. And there you have it. So you're moving from, so we moved from L, liquid phase, through to, as it was cooling at this composition, isn't it? So it moves from L to alpha plus L, which is at point B there. Then finally, we came to the alpha phase, the solid phase. So solidification proceeds in the same manner as for isomorphous alloy, Vg, copper, and nickel. Oh, that's a time. Okay, coming to this one, it's the same alloy, except now we've moved where